Hi, I'm meteorologist Andy Hayner with the National Weather Service in Seattle. And this presentation is going to highlight a distinct local effect. It's unique to mountain ranges along the west coast of North America, including the Olympic Mountains and the Cascades, as it involves the movement of marine air into and out of these mountain ranges over the course of the day and night, and the interesting effects that it has on relative humidity and fire behavior trends over the course of the day and the night. So, a quick review. This is a snapshot from the S290 course, which it just shows the traditional relationship between temperature and relative humidity. And the upshot of this is that in most places, on most days, you can expect temperature to go up in the afternoon and relative humidity to go down in the afternoon. And then at nighttime, temperature falls and relative humidity rises. However, when you're talking about a regime near the top of the marine layer or near the edge of the marine layer, this relationship can fall apart. Let's take a closer look. So from the S290, this is just a little refresher on what exactly the marine layer is. And the marine layer is just a relatively shallow, cool, stable layer of moist air that forms over the cool waters of the Pacific Ocean during the summertime. This is the time of year when the sea surface temperatures are typically 48 to 60 degrees, while higher up in the atmosphere you have summertime air aloft, but down close to the surface you end up with this layer of cool, moist, stable air. And that layer of cool, moist, stable air tends to spread inland onto your coastal plains, past your coastal hills or mountain ranges, and into inland valleys such as the Puget Sound lowlands or the Willamette Valley, before finally being intercepted by a bigger mountain range such as the Cascades in Washington and Oregon. So during the daytime, as the land heats up, it tends to draw more of this marine air in, and at night, as the land cools down, it tends to draw less of the marine air in at night. So now we are looking at a vertical cross-section of the marine layer. Again, I mentioned earlier that the marine layer is a shallow layer of air. So within the marine layer, it tends to be about 60 to 65 degrees, for example, out along the Washington coast on a typical summer afternoon. But once you rise up and out of that shallow marine layer of air, you're basically up in warmer and drier summertime air aloft. In fact, as you work your way out of the marine layer and east of the Cascades, it can be over 100 degrees on many summer afternoons. And just as it gets warmer outside of the marine layer, it also gets drier, with dew points that can run anywhere from 10 to 20 or 30 degrees lower outside of the marine layer than inside that cool, moist, stable marine layer. So really what this presentation focuses on is what happens if you are right there near the edge of the marine layer, where you have the marine layer sometimes sloshing in and sometimes sloshing out. So that's what we're really out to talk about here. Just to help you better visualize what the marine layer is, here is a picture that pretty clearly demonstrates this. This is looking south from Victoria, British Columbia toward the Olympic Mountains across the Strait of Juan de Fuca. And you can pretty clearly see that cool, moist, stable marine air down near the ocean surface and what appears to be warmer and drier air up above as you look up toward the Olympic Mountains. Here's another view of the marine layer, this time from Camp Muir, which is up around 10,000 feet on Mount Rainier. It looks like this is looking south toward Mount Adams. And you definitely see that marine layer of clouds that has worked its way up the Cowlitz Valley, which is between Mount Rainier and Mount Adams. Okay, so let's talk about some daytime and nighttime influences on the marine layer. First of all, when we're talking about the marine layer over land, the marine layer tends to deepen during the day. This is owing to the fact that you get daytime sea breezes going, up valley breezes going in your mountain ranges, and upslope breezes, which advects or brings that cooler and moister air inland and up your mountain valleys. At nighttime, the opposite happens. You develop land breezes and down valley breezes, and downslope breezes, and those breezes tend to flush the marine air back out over the ocean or out of your coastal mountain ranges at night. And it's also important to note that just because clouds dissipate, your marine clouds dissipate over land during the daytime or during the afternoon, does not mean that the marine layer is gone. I hear people talk about the marine layer burning off. Well, the marine layer is still there. It's just that the air mass is no longer saturated to the point where you have fog or clouds. So you still have that air mass that's in there. It's just that the clouds dissipate. Here are some synoptic influences or large-scale influences on the marine layer. Marine layers tend to get shallower as you build upper-level high pressure over a region. Upper-level high pressure tends to weaken onshore flows, so that's part of the reason that the marine layer gets shallower. You're just not bringing in as much marine layer or marine air off the ocean. By the same token, the marine layer gets deeper as an upper-level trough of low pressure approaches. That tends to strengthen your onshore flow, and that basically pushes more marine air up onto land. So as we dive into more detail on the unconventional effects that the marine layer has on relative humidity and fire behavior, I also want to point out that that these effects are most pronounced late during fire season or during the second half of fire season, basically from mid and late August on through September, and as late as it takes to end fire season in a given year. Okay, so here's the first of two case studies. This is a case from September 24th, 2009. Actually, that's when this satellite picture was taken. This is looking over Oregon, and you see marine clouds that have worked their way in off the ocean, and on this morning are filling the Willamette Valley with marine clouds. Meanwhile, down at the southern end of the Willamette National Forest, you actually see a lot of wildfire smoke. That was partly from the contribution of the tumblebug complex, which was going on at that time. Now, a few geographic landmarks that I want to point out here. First, I want to point out Salem. I want to point out Salem because that is one of the places in Oregon where weather balloons are let go 2 times a day. And then I also want to point out the location of the immigrant Ross site. That was close to the location of the tumblebug complex and was also pretty close to the top of the marine layer. So here is data that's plotted from an upper air sounding at Salem, Oregon on the morning of September 25th, 2009. And what you need to know is that on this plot, the black line to the right is a representation of temperature, and the black line on the left is a representation of moisture. And so you very clearly see the marine layer down low on this sounding, where the temperature is cooler and the amount of moisture in the atmosphere is higher. So it's interesting to note that just below the top of the marine layer, this sounding showed that the temperature was 54 degrees and the relative humidity was 90%. But by going up just a few hundred feet in elevation, up and above and out of the marine layer, the temperature rises to 64 degrees and the relative humidity drops to 3% in just the course of a few hundred feet of elevation. That's pretty amazing. As we continue on with this case study, I'll show you conceptually how the marine layer affected the relative humidity readings at the immigrant Ross site, which was near the top of the marine layer, and some of the effect that it had on fire behavior at the tumblebug complex. Now, there was a period of about 3 days in late September that year as the tumblebug complex was going, where marine air spent about 3 days just basically sloshing up and down this valley. So during the daytime, you would get up valley breezes that would develop and bring air that was down in the main Willamette Valley down near Eugene. It would bring this air up the valley so that by later in the afternoon, you would get that cooler, moister, and more stable marine air up and over the immigrant Ross site. And then at nighttime, that marine air would basically slosh back down the valley owing to the effect of down valley breezes, and eventually by late at night the immigrant Ross site would find itself in the warmer and drier air outside of the marine layer. Now this is just a picture of the immigrant Ross site showing how it's on a low hilltop within this larger valley, so it's considered a mid-slope site. Now these are the dew point observations from the immigrant Ross site over the course of this 3-day period when the marine air was sloshing in and out. Where you see yellow shades, those are daytime hours, and then the bluer shades are nighttime hours. And you can pretty clearly see where you were getting these afternoon and early evening spikes in the dew point readings as the marine air got sloshed up the valley, and then you would have these sudden dips in the dew point, or basically the amount of moisture in the air late at night as the marine air flushed back out of the valley and the immigrant Ross site was suddenly back in the warmer and drier air just outside of the marine layer. So these afternoon peaks were generally coming anywhere between about 2 p.m. and midnight. That is the time of day when the moistest air was coming up into this Ross site. And then your driest air of the day, at least in terms of the dew point reading, was coming in the hours right around sunrise, 5 a.m., 6 a.m., 7 a.m. Those were the hours of the day when downslope breezes had the marine air flushed as far down the valley as possible. Okay, so that was dew point, but what about relative humidity? Well, even in the relative humidity trace, you see these drops in relative humidity that were taking place during the late night and early morning hours. Now, I was an IMED on this fire, and one of the things I can remember was hearing the night shift come back in, and they would talk about how quiet the fire was during the late evening hours, but then late at night, like at around 4, 5, 6 a.m., the fire activity would suddenly pick up. Well, with a relative humidity trace like this, you start to understand how fire activity in this kind of environment can actually pick up during the late night and early morning hours instead of decrease like you conventionally expect. Okay, so now we move on to the second of 2 case studies. And this is just an upper air sounding from Quileute, Washington, that's out along the Washington coast, on the afternoon of Monday, May 9th, 2011. Here is a satellite picture, actually from the next morning, but basically the same kind of pattern was in place. And you see the marine layer clouds surrounding the Olympic Mountains. You can almost picture how the Olympic Mountains would stick up and out of the cool, shallow marine layer. So what happens is during the daytime, you start to develop up valley breezes in the valleys of the Olympic Mountains and pretty much any coastal mountain range, and that actually starts to draw marine air into the interior of your mountain range and up into higher elevations. And then at nighttime, the opposite happens. You start to develop downslope and down valley breezes, and that flushes your marine air out of your coastal mountain range and back out, basically back out to sea. So here's a conceptualization of a fire burning at a higher elevation in a coastal mountain range. You start off with the marine layer in place down near the bottom of the mountain range, but warmer, drier, and more unstable air in the higher elevations of the mountain range. So you start off with a fire burning in that warmer, drier, and more unstable air. So basically, the fire is burning actively. So let's say it's 9 o'clock in the morning. The sun has come up, and you're just starting to get your upslope breezes developing. And by later in the morning, you start to get up valley breezes, pulling that cooler, moister, more stable marine air into your coastal mountain range. Well, by 3 o'clock in the afternoon, the marine air has actually deepened over your coastal mountain range. And that marine layer eventually overspreads the elevation where the fire is at. So as a result, what had been a big fire to start the day with, well, basically the fire behavior starts to subside and become more timid during the afternoon. Okay, so now it's 9 o'clock in the evening, and in the summertime, the sun has just gone down. And so you start to develop your downslope and down valley breezes. And so that starts to flush your marine air out and away from the mountain range, and the marine air starts to become more shallow over your mountain range. So by the time you advance to 3 o'clock in the morning, your marine air has flushed out of the mountain range, and that higher elevation fire is now back in the warmer, drier, more unstable air that is over on top of the marine layer. And as a result of entering this different air mass, the fire basically gets bigger. The fire behavior starts to increase during the late night hours under this kind of setup. This is just a readout of weather observations taken at Hurricane Ridge, which is up around 5,000 to 5,500 feet in the Olympic Mountains. And this is looking at early May of 2011. And so you'll read this from bottom to top, and what you see is that in this example, at 9 o'clock in the evening at 2100, you have a relative humidity of 91%. Well, during the overnight hours, without a whole lot of wind, your relative humidity takes this plunge during the late night hours, such that by 5 o'clock in the morning, your relative humidity has dropped to 32%. After the sun comes up, you actually start to draw that marine air back into the mountain range, and your relative humidity actually rises during the morning after the sun even comes up. And by noon, your relative humidity has risen to 51%. So here is one more example from Hurricane Ridge. This is from late September of 2010. And this is an example where if you start off at the bottom, you start off at that first observation at the bottom is from 11 o'clock on a September evening when the relative humidity is 78%. Well, during the overnight hours, this is one of those cases where the marine air got flushed out of the mountains and your dew point just plunged. You even got rising temperatures in the hours before sunrise. And by sunrise, your relative humidity had dropped to 10%. Started off the evening at 78%, into the night at 10%. Wow. And moving on, after the sun comes up, you start to pull that marine air back into the mountain range, such that by 1400 or 2 o'clock in the afternoon, your relative humidity has risen to 44%. Now, this is a fairly extreme example, but it does a nice job of at least illustrating this effect. And even by the end of this example, by 10 o'clock that evening, the relative humidity has dropped back to an amazingly low 3%. Out in Olympic National Park in September of 2003, there was the Griff Peak Fire. In fact, if you drive up to Hurricane Ridge sometime and look out to the north, you will see the burn scar from the Griff Peak Fire, which occurred in September of 2003. I happened to be up at Hurricane Ridge in October of 2011 and took this picture of the burn scar that is up there. In fact, on this October afternoon, you could even see we were right at the top of the marine layer, and you could see the marine clouds getting drawn into the mountains. So you can kind of see how the top of the marine layer is advecting in or getting wafted in over this old burn scar. So old-timers out there tell me that this fire actually was a nocturnal burner. Basically, this fire underwent its most active burning during the late night hours, and then it would just lay down during the afternoon hours and then pick back up again at night. So hopefully what you've learned in seeing this picture helps show you how this could happen. Here is a picture of the big Hump Fire on the Olympic Mountains from 2011, and it's a pretty nice example of a fire that is burning both above and below a marine inversion. So the portion of the fire that's burning below the marine inversion, you see the smoke getting trapped in that valley and not being able to go anywhere. In fact, the fire burning beneath this inversion was just creeping and smoldering that day. Meanwhile, the portion of the fire that was burning above this inversion, you can see the smoke was lifting out and spreading away. And field observations from that day showed that the upper part of the fire was burning most actively with group tree torching on this day. This is actually a picture of the same fire from the same day, but just from a different vantage point. And again, you see how the portion of the fire burning beneath the inversion, the smoke was just getting socked into that valley, while the portion of the fire burning above that inversion, the smoke was lifting out, the fire was getting plenty of oxygen, and it was burning quite actively. So the effect on relative humidity forecasting is that if your fire is near the upper edge of the marine layer, you want to be expecting unconventional daytime and nighttime relative humidity trends. For example, you could end up with large drops in dew point and therefore relative humidity during the overnight hours when you are most expecting dew point and relative humidity to rise. By the same token, if you're near the top of the marine layer, you may find yourself experiencing large rises in dew point and rises in relative humidity during the late morning and afternoon hours if that marine air sloshes back into your location in the afternoon. So when this kind of phenomena takes place, you're most likely to get your maximum relative humidity around 9 to 11 o'clock in the evening, not 5 to 7 o'clock in the morning when you most conventionally expect it. In fact, under this kind of pattern, you can get your minimum relative humidity occurring between 8 and 10 o'clock in the morning, just after sunrise, not at 3 to 5 o'clock in the afternoon when you most conventionally expect it. So that's the end of this topic on relative humidity and fire behavior trends at the top of the marine layer. I hope this has been enlightening, and if you find any examples of this while you're out in the field, this is a topic that I find particularly interesting. So feel free to email me at andrew.hainer@noaa.gov. Thanks and have a safe fire season.